Okay, so this week we're going to do time constant of LR circuit. So what is L? L is what we call inductor. This is the diagram of the circuit. So you can see that you have the battery that output energy, and you have the switch, and you have the resistor, and this symbol, the coil, indicate this is an inductor. Okay, well, what's going to happen is that if you switch off, meaning that you have the current that go through, you use the battery or power supply to power the circuit, then there's a current that's going to run through the circuit. Now, initially, the current is not going to be a constant. You're going to find that the current actually follow this form. So it takes some time for the current to reach a steady state. Is what we call when it reaches the maximum value. And the inductor is a device, basically it consists of a coil, and with the main goal that it can store magnetic energy. We know that a resistor is the one that dissipates energy, and this one store magnetic energy. And capacitor is used to store electrical energy. So as you can see, when you switch up, the current increases in time, and then it reaches the maximum value. And then when you power down, let's say when you switch down, meaning that you remove the battery from the circuit, then what you're going to find is that the energy stored in the inductor is going to power the circuit. And then the current is going to decrease in time because the resistor is a dissipating device. So you can see that the current as a function of time is going to decrease in time. So the equation that can describe the rise and fall of a current can be you can apply Kirchhoff's rule, and what we have here, equation 2, you can see that this is the voltage of the battery, and then this involves the resistor, so minus IR, and then minus what we call the back M, indicating that when current increases, the coil is going to induce a back M. When we say back M, it means that a self-induced M. It just means that it's going to induce a voltage to oppose the rise of the current. Okay. And so you can see that minus L and then di over dt. So this term indicating that when current changes with time, then this is going to be non-zero. Okay, and so this is what we call the back M, and this is the expression, and that is minus L di over dt. And of course, we know that in time, the current is going to reach a steady state, then this term will become 0, okay? But before that, then there's going to be a back M in the resistance in the inductor. So anyway, so when there's a battery in the circuit, you have the M minus IR minus L di dt. As you can see, this is the first order differential equation, and with the source term. So we can solve for the current as a function of time, and we found that the current as a function of time is the voltage of the battery over the resistance, and then times 1 minus e to the minus r over L times T. And L here, I forgot to mention, is the inductance of the inductor. Okay, and R, of course, is the resistance of the resistor. So you can see that the current is not a constant. The current is actually a function of time, and is proportional is actually can be described by this expression. So you can see that when t equals 0, there's no current. When t approaches to infinity, then it becomes just n over r. Then if we remove the battery from the circuit, then the equation will become like this. But before we do that, let me just say that the voltage, when the battery is still in the circuit, the voltage across the inductor has this expression. That's minus M, which is the voltage of the battery or the power supply, and then e to the minus r over L times T. Okay. Now, when we remove the power from the circuit, then of course there's no source term. You still have the first order differential equation, and you're going to solve for this solution for for current, and the current will have this form. I don't know why it's not showing. Interesting, but anyway, the current will have the current will have the N over R and then times, just ignore this 1 minus. So in the lab packet, I mean, this is correct. So you have the N over R and then e to the minus R over L times T. And then the voltage will take up the same form, but then without the minus sign in front of it. That will be for equations 6 and 7 respectively. Anyway, all right. So when we look at this, you can see that the current is a function of time. This is for the rise of the current. This is for the current, and we can actually find characterize the time that it takes for the current to reach a maximum or decrease to a 0, and and that quantity is what we call the time constant. So time constant we use tau, a Greek letter, to indicate as a time constant, and can be calculated using L over R. Okay, and so this will have the units of in seconds, as you can see, because in the argument, the exponent here has to be by dimensionless, and if you have the time, t is time, so that's in seconds. So the R over L has to be per second, meaning that L over R will be in seconds. So this is time constant, can be calculated for inductor, L over R. You just want to make sure that everything has to be in SI unit. So the units for inductance is in Henry, but most likely when you measure the inductance in the lab, it will be in milli-Henry. So you have to convert that to Henry before you do the calculations. Okay, and what is the significance of the time constant or physical meaning of time constant? It is exactly the same as the as in the RC circuit. It just characterize how much time it takes for the currents to reach 63% of its maximum value when you have the rise of the current, or how much time it takes, the amount of time it takes for the current to decrease to is 37% of the initial value if this decreasing if this from the decreasing segment. So in other words, you just plug in the equation, you just plug in 1 time constant, 2 time constant, and that will tell you how much current is remaining in the circuit. Okay. So so that's basically the physics of the LR circuit. Now, regarding how we set up the experiments, so this on the electronic board, you're going to use this side of the electronic board when these two are going to connect it to the interface output. So we're not going to use the power supply to power the circuit. We're going to actually connect this to the interface, the black box, of the on the interface on the black box. So these 2 wires is going to connect to the power supply from the black box. And this is what we call the inductor. So yeah, we're going to have like 2 scenarios. One is that this is just inductor itself, and then the second one is that we're going to put an iron core, inside the hole of the inductor to enhance the inductance value. So you're going to measure the inductance of the inductor with and without the iron core. You'll find that the values will be different, even though you're measuring the same you're going to measure the same inductor, but then with or without the material inside the hole will change the inductance value. So you're going to measure that. Now, when you measure the inductance, make sure that you do not power the circuit. So this should be use of a voltmeter to connect to this spring, before you do anything. And then so measure that, and then you set up the circuit. So you should have 1 wire lead connecting this spring to the spring. You should have another wire lead from this spring to that spring. This 2 connected to the black box, and then you have the resistor right here. Okay, so you can see that this forms a series. And we want to measure the voltage across the inductor. So these 2 are going to connect to channel A on the black box. So this is we're going to use a voltage sensor. So we're not going to use a voltmeter to measure the voltage. We're going to use a voltage sensor that's connected to the black box. So after you set up this, you also need to calculate the time constant, and then calculate 10 times the time constant. And then you're going to key in the frequency in the computer, in the system, in the program, and that frequency is we're going to use a frequency that's 1/10 times the time constant. This value of the frequency will give you a nice looking, rise and fall of the current. So, so the frequency that you keyed in is not 1/tau, it's 1/10 tau. And we're going to choose a positive. I think the default is that it is the program default is positive square wave, and the amplitude is at 5. So we can double check that if this is the correct setting. And the resistor value will have 100 ohm. And once you set everything up, then you want to click the on button on the signal generator panel, and then you hit record, and then the program will start running, and you're going to generate plots like this. As you can see, because we use a square wave, and then when we measure the voltage across the inductor, we found that the voltage in the inductor were the voltage is actually rise and fall, rise and fall. So there's what we call the decreasing part, and you have the increasing part. Because we're actually using the AC circuit, that's why you don't see so we have the downward, the decreasing and the increasing. Okay. So once you have generate the plot, and then generate this on the oscilloscope, you can change the arrows here to increase or decrease the divisions to make it so that you only have one or two pattern on your oscilloscope. And then you want to click on single trace that is on your on the panel. And so this one will shows that it was kind of like freeze the screen. So you only have, so it doesn't like sweeping all the time. So once you click on the single trace, and you're going to have just one pattern like still pattern like this. And then you're ready to so you want to do one with the do one with the coil, one without the coil. So once you get one data, before you move on to with the coil, you want to follow the steps in the analysis. You want to click on this data selector, and then choose the run, because you might do several runs. Choose the run that you want to process your data, and then you're going to and then you can use this highlight the data that only involve the decreasing process, and you want to click click on this. This is the fitting. You want to use the natural exponent fit. So in other words, once you have that on your oscilloscope, you want to select you want to use a highlighter to select the data that will be fitted. And then so once you highlight those regions, do not include the astral data points, otherwise you're going to mess it up. So just highlight the part that involves the decreasing, and then you choose and then use this function to choose a natural exponent fit. And then once you do that, the program is going to return. It's going to return a value that return a form that's very similar to this. So it will actually, instead of saying V that's equal to this is actually going to say, I can't remember, but I think it's Y that's equal to the A and then times e to the minus B X and then plus C. Okay. And that here is the voltage across the across the inductor, because remember the voltage sensor is across the inductor. So you're going to get an expression like this, and you want to write down your line your curve fitting expression exactly like this, but with your own values. So you have the VL of t that's equal to whatever that you have in front, and then times e to the minus whatever that you have in the in that, and then replace your x by with t, and then plus whatever that you have here. Okay, so this is the part for the decreasing. Once you jot down those, then you can highlight the data involved in the increasing process. So in other words, you can highlight. So once you're done with the decreasing, then you highlight the increasing part, and then you will follow the same process. Choose a natural exponent fit. And then it's going to return the this kind of expression. So jot down your values, replace whatever value that you have. So just whatever value that you're getting, just replace the ABC with whatever value that you have, and then you're done with the with the line fit. So the table. So for the without iron core, you will have the decreasing. You will just write down V. You will write down something like VL of t, and then whatever value that you have times e to the minus whatever you have here, and then this is time, and then plus whatever value that you have. Do the same thing for the decreasing part, okay? And then for the time constant, theoretically, we know that is equal to L over R. So you want to punch into a calculator to calculate L over R. And realizing that, for the same circuit, that doesn't change for the decreasing or increasing part. So you should have the same value here, okay? Experimentally, how do we find the experimental value of the time constant? If we have, let's say, if we call this B, then the time constant experimental value is equal to 1 over B, okay? So you can see that for the decreasing and increasing, this value will be different, primarily because it depends on how you fit your data. So you have one value there, so you can calculate the percent error, okay? And you would do the same thing. You would do the same thing for the, with the encore. So basically, what I want to see is the voltage, you want to express your expression like exactly like this. V sub L of, of t is equal to your value times e to the minus your value t plus your value, okay? And do the same thing for the increasing. Now for this table, you would measure your resistance, and then you would measure the inductance, your in Henry's, and then you want to calculate, and based on the value, you want to calculate your time constant, and that time constant, of course, is what we call the theoretical value. So this is the frequency here that's going to key into the program, so I can generate the pattern. Okay, so that's basically what you want to do today, and then once you have once you have those, then you can calculate the percent error. Okay.